let's talk how extension 2 makes integration more difficult. So there are a few different ways, and you've already touched on some of them, right? You've looked at some integration by parts, techniques, and stuff like that. And in terms of like a scale of integration in general, if you do maths at uni, you'll see that like this is just the tip of the iceberg. Like you can keep going down this rabbit hole of what kind of integration techniques and strategies there are, right? Yeah, the Confucius wise wisdom. In extension 2, the first thing that they start you off is we look at the fact that when we looked at integration in extension 1, we gave you substitutions to use and you applied them, okay? Now extension 2, there are some questions which they give you substitutions, but there are a lot of questions where they don't. And the strategy for picking substitutions probably comes with familiarity. When you've seen enough problems, you tend to know what kind of substitution makes sense. And you probably got a sense of that when you looked at extension 1. So I guess when we're going to look at substitutions first of all. And I suppose a helpful tip is, yeah, we want familiarity. So I can't really like teach you that. That's just something you got to do. In terms of stuff I can tell you, I guess look for, this is not going to sound that helpful, but look for what's complicated. Yeah. So we're going to look at substitution first. No, that's the first one. Yeah, so we call it a U substitution. That's just because we use the letter U to represent that, right? Okay. And we want to look for what's complicated to try and make this question more approachable. Another thing I want to note is that when you have sums or differences of square roots, okay, not just any kind of square root, but a sum or difference of square root. Okay, so that may be something like this, or something like this. You might actually recognize these from certain places. If you think back to your inverse trigonometry, that looks like a component of that, right? So a helpful substitution, whenever you see a situation like this, is either u is equal to a sine theta slash a cos theta. I typically just do sine, or u is equal to a tan theta. That's going to be helpful as well. Okay, that's something that can help you out there. All right. Okay, and typically we want the substitution in terms of x. So yeah, that's just pretty self-explanatory. All right, let's give you an example. Let's look at this guy. That's all I've got to give you as a head start. Let's find this guy. We want to pick a substitution which helps us uncomplicate this expression, and we also want to somehow relate to sort of both these terms, because we know that when we do make a substitution, we also want to replace this dx with whatever the substitution that we have is. Let's try. So you want u is equal to 1 plus cos x. Yeah. So du would be equal to negative sine dx. Okay. And what do you want to do that? Yeah, right. So that one's not too bad, right? So you notice that when you take the derivative, that allows you to access this part here now, right? We do need this negative here. Okay, so we'll put that in. But then after that, we can straight up do the substitution. So we've got negative. So this negative sine x dx is this part over here. I'll replace that with du, or 1, right? And then denominator, what do we have? We've got u cubed. And that's quite nice, yeah? So we're just going to integrate this guy. So something like this. Is that what you guys got? A couple of things to note. When you put that in, just be aware that when you have this expression, we live in terms of u, we do want to leave it in terms of our original question, because this is asking us to find this, right? This is not really a complete answer. So we just finish it off, and we have 1 on 1 plus cos of x all squared, plus our constant. Okay. So like I said, the main difference for a lot of these integrals is they're not going to give you the substitution. You're going to have to try and choose one yourself and see if it works. If it doesn't, you're going to have to go back to the drawing board and try something else, right? Let's look at another one. Let's try this one. That's our first example. So that's x squared here, this whole thing. So what do you want to try? U is equal to... I guess the idea is there's no harm in trying something and seeing what happens, right? X? You want to try X? Yep. X squared, you reckon? Yeah. Yeah, sorry. Was it meant to be 1 on 2? Sorry, negative, I think it should be negative 1.5 over here. 1 on, no, it's 1 on. So it should be negative out here as well. Negative, divide by the new power, so divide by 1, 1 on negative 2. So there's a negative stay there for that? Yep, sweet. All right, good thought. Cool. So there should be a 2 here as well. Okay. Yeah, so that's the right answer now. So, okay, going back to this one. Angus suggested, hey, let's use u is equal to x squared. Let's try it, okay? Du is going to be equal to 2x dx. And then the advantage of choosing the substitution, which you've done, is that when I use it, not only can I make this part simpler, I can also access this part as well. Because that's what you want to be thinking about. You want to think about, okay, how can I make the whole expression less complicated, but also how can I incorporate this du that I need to substitute in? And we can see that here, right? All we need is this 2 here, and so we have the half outside to address that, undo that operation that we just did. That half can stay there, and then when I make my substitution, I'm going to get 1, oh sorry, not 1 this time, we're going to, oh no, we do get 1. 1 on e to the u, du, right? So that 2x dx just becomes du. I like to put it there just because it's easier to read. And so I'll try not to make mistakes this time with the integration. So I'll rewrite it in index form, and then we'll get negative e to the negative u. How's that look? And we should probably write this in terms of x as well. All right. How do you like that? You got that? Okay, cool. All right. So that's all well and good. But so far, these have all been indefinite integrals. So let's mix this up.